This is the first video from chapter 8, which is all about kinetics. And the first thing I want to do is introduce you or reintroduce you to energy profiles for chemical reactions. It's something you should get real familiar with. Note that along the y-axis is energy. A lot of times it's delta G. Sometimes you'll see it as delta H, but usually delta G. On the x-axis is reaction progress. So notice that the reactants are represented to the far left and the energy of the products represented to the far right. All right, so energy profiles tell us a bunch of things, but two of the most important things they tell us is how fast a reaction will go. And you'll learn as we go through this PowerPoint that the rate of a reaction is dependent on the size, the magnitude of this first little kind of hump, which is called activation energy. And when we start talking about rates, we are talking about the kinetics of a chemical reaction. All right, so now the free energy, excuse me, the difference in free energy between the reactant and product, so delta G, is information we've talked about before. That tells us whether or not a reaction is spontaneous. Delta G does not tell us anything about how fast or slow. Okay, so again, just quick summary. This top little hump tells us about the rate or kinetics of a reaction, and the bottom portion, the difference in energy between the reactants and products, tells us whether or not a reaction will actually occur, whether it's spontaneous, how much product will be formed. Alrighty, so just to make sure that I've emphasized that the rate of reaction has nothing to do with its spontaneity, I just wanted to give you all different scenarios. You're probably familiar with iron rusting, right? That is a spontaneous process. So if you leave a chunk of metal out long enough, you will see rust building up. You don't have to do anything special to get that rust to form. So that is a spontaneous reaction. It has a delta G that's negative, but it is very, very slow over a period of years, okay? We also do have spontaneous reactions that are also very, very fast. And we have non-spontaneous reactions that are relatively fast and slow once you get them started also. Just a kind of a quick overview of some of the basics we've learned about chemical reactions. The one I want to point out is, or the bottom two actually, is that reactions are always accompanied by an energy change. And the value of delta G free energy tells us whether or not a reaction is spontaneous. All right, so just kind of, this is testing prior knowledge. What thermodynamic function tells you about how far a reaction will go? I want you to pay attention to this vocabulary because I think on multiple choice questions, that's what throws students off. So if I were to ask you whether or not this reaction is spontaneous, I think you could probably pretty quickly answer it, right? You'd say, okay, delta G is negative. I can tell because the energy of the products is lower than the reactants. But what if instead of spontaneous, I said, are reactants or products favored? Which is favored? Would you be able to answer it then? Well, what I want you to realize is if products are favored, we are talking about a spontaneous reaction. If reactants are favored, we are talking about a non-spontaneous reaction. So just because a reaction is non-spontaneous doesn't mean we will get zero product. It's kind of a statistical outlook on it, that you imagine reactants, and if it's non-spontaneous, that means, I'm just going to redraw over here. So if it's a non-spontaneous reaction, the energy of the products is going to be higher than the energy of the reactants. But that doesn't mean we won't get any product, okay? So if you consider reactants over on the left, every now and then one is going to find enough energy to make it over the activation energy hill and become a product. So it's just that reactants will be there in larger quantity. So the answer to this question, what thermodynamic function tells you about how far a reaction go, that's another way to say how much product. What thermodynamic function tells you how much product will be formed? It is delta G. What thermodynamic function tells you about how fast a reaction will go? This one you might question because I just mentioned it for the first time. That is the difference in energy. It's the top part of these energy profiles. Difference in energy between the reactants and the highest energy point. That is called activation energy. And activation energy is not on here. So the correct answer to this one is none of these. All right, so activation energy, it is abbreviated capital E sub A. Again, is the difference in energy between the reactants and the highest energy point of that reaction. This particular energy profile has two humps, and that is because this is a two-step reaction. Every step in an overall reaction has its own activation energy. And the higher the activation energy, the larger the activation energy, the slower that reaction is. Okay? So imagine this is you down here and somebody tells you to go as fast as you can over this mountain. It's going to be harder and take you longer to get over this big mountain than it will the second one. So this first step is the slower step of these two. And this one is the faster step because it has a lower activation energy. Now, if you're comparing two reactions, let's say they're both spontaneous, but one has a much smaller activation energy than the other one. So I would ask you, which one is spontaneous? You'd say, okay, both of them. Which one is the faster reaction? Well, that would be the one with a lower activation energy. So make sure you can not only interpret these graphs, make sure you can sketch them. If I tell you it's fast and spontaneous, you should be able to draw it. If I tell you it's fast and non-spontaneous, you should draw it and be able to label each part of the graph. All right, I want you to think specifically about an acid base reaction. So we're going to take a strong acid and we're going to put it in water. So we'll get hydronium ion and the conjugate base. We know that's a strong acid. And so if you remember the definition of strong acids and base, they dissociate 100%. So the instant we put this in water, this is all gone and we have 100% the ionized form of it. And it's spontaneous and it happens very fast. So that would be like this. Okay, spontaneous, probably might have a lower activation energy, but regardless. So now, if you see that an acid or a base described as strong, these are all the different kind of descriptors that would apply. That would mean it's reactive. That would mean the reaction is spontaneous. That would mean products are favored. All right. And now let's think about a weak base. So we know acetic acid is a weak base, so I will try that. And I'll dump some acetic acid in water. And I'm going to draw the reversible reaction, which is typically what we do for weak acids and bases. So we're going to have acetate, the conjugate base, and then hydronium ion. Okay, so For any weak acid or weak base, it is not very reactive, and therefore it's also non-spontaneous. Again, that doesn't mean we will get zero product. It just means we won't have very much product. So we would say reactants are favored. Okay. So any reaction where reactants are favored would be a non-spontaneous reaction energetically. Any reaction where products are favored would be a spontaneous reaction. There's kind of a lot of vocabulary in this, so just be careful with it. All right, let's just look at a couple more graphs, then we'll move on. So let's say I gave you this graph and I asked you to describe it as far as speed and spontaneity. Well, first of all, hopefully right away, you can see the delta G is negative and therefore it's a spontaneous reaction. Probably most of the time you'll be asked to compare two energy profiles. And so it's very clear that the activation energy of the reaction on the left is much larger than the activation energy on the right. So this is a slow, spontaneous reaction. Let's look at the one on the right. It is also spontaneous, okay, because delta G is negative, but it has a much lower activation energy. So we would call this one faster. So what if I asked you which one of these are products favored? Hopefully you would say both. They're both spontaneous, right? Which one are products favored? Both. Alrighty. All right, let's talk about reaction rates. Rates of reactions now. What is a rate? Well, rate of anything is the change in something per unit time, right? So what's changing in a chemical reaction? Well, it's the amount of the reaction and reactant and product, okay? So if you have A plus B reacting to give C plus D, you could monitor the disappearance of either reactant, or you could monitor the appearance of either product over a period of time. Since most chemical reactions happen in solution, the amount or the quantity of reactant or product is typically in units of molarity. So molarity, moles per liter. So for the most part, reaction rates are expressed as change in concentration of any reactant or product over change in time. So here's a really simple example of finding a reaction rate. Here's the question if you want to read it for a minute. Now you need to remember that the rate of a chemical reaction, as we just went over, is the change in concentration over the change in time. So reread the question and let's see if we can figure out what rate is. All right, concentration changes from 1.5 to 5. 0.5, sorry. So the concentration has changed by 1 molar. And the amount of time gone from 0 to 10 seconds. So the change in time is 10. So let's just put units there too. All right, so that tells us that the rate of this reaction is 0.1 and the units are molarity per second. These are always the units for rate that we're going to use. So just get used to that, molarity per second. Sometimes you will see it written out. Molarity, of course, is moles per liter. So sometimes you will see it as moles over liter times second. And of course, time doesn't have to be seconds. Sometimes it can be minutes. All right, there are several graphs when chemists are talking about rates of reactions. you'll see a lot of graphs. So this is one of them. But I want you to look at it for a minute. Keep in mind that rate is on the y-axis, time is on the x-axis. What is happening to rate as time goes on? So rate is decreasing, which most reactions do. Most reactions have a rate that decreases over time. Why? Why would the rate decrease? Why would it get slower over time? Well, what's happening to, remember what rate is? Okay. Rate is change in concentration of reactants or products over time. The actual amount of reactants we have is decreasing over time. And later on, we'll talk about something called the collision theory, which tells us that two reactants literally have to collide with each other in order to react. So if you have fewer reactants, you're going to have fewer collisions and fewer actual reaction. So the rate typically does decrease over time. So there are several different types of rate. What we just calculated was the average rate. So that was the rate of the reaction taken over some extended period of time. We also have something called an instantaneous rate. And that is, what if I were to ask you, what is the rate of reaction at exactly 3 minutes? So that's done a different way. So we're going to talk about the two. The average rate, first of all, wait a minute, look at these graphs. They're a little bit different than the one on the last slide. On these graphs, instead of having rate along the y-axis, we have concentration along the y-axis. And time is still along the x-axis. So I'm going to put here we go. The expressions for rate are up here, okay? I'm just going to write it bigger. Is change in concentration over change in time. Okay, so concentration is on the y-axis, time is on the x-axis. So what is rate? How can you get rate out of these graphs? It is the slope, okay? So the change in concentration, so let's say we pick two different concentrations, okay? So this is the change in concentration over this amount of time. All right, so this would be the slope of this from in this area, right? Right, so this slope would be the average rate over that period of time. Now, again, let's go back to what if I asked you, I want the rate of the reaction at specifically this moment in time. At that point, and for those of you who have taken calculus, an instantaneous rate is this, you would draw a tangent line on that curve, and the slope of that tangent line would give you the instantaneous rate. So let's kind of check your understanding. Look at the graph with the three different colored lines. There's a red one, green one, blue one. And here, hold on. Let me show you pick a different color here. The reaction itself is represented by this curved line, the black line, now yellow. All right, so now which of these lines, the green, red, or blue, represents an average rate? I am hoping that you picked the blue one. Why is the blue an average rate? Well, it might be easier to kind of work backwards. The red line and the green line are tangents. They touch, or they're supposed to touch, the curve at only one point. That makes it a tangent line, okay, which makes it an instantaneous rate. But perhaps more important than that, look at the blue line. The blue line tells us the change in concentration over the entire reaction period. Okay, so this blue line represents the average rate over the entire reaction. All right, now answer this question. Which rate is the fastest? Is it the green line, the red line, or the blue line? And again, let's look at the equation for rate. Change in concentration over change in time. Which one is largest? The larger the rate, the faster it is, right? It is the one with the largest slope. Okay? So that means the one with the largest change in concentration, right? All right, so hopefully you can now look and see that the green line has the largest slope. Okay, it's got quite a bit of change in Y value or concentration for just a small change in time. Alrighty, so now we know the generic expression for rate, change in concentration or change in time. And look at this particular reaction. This is, no, it's not combustion. I did that before. It's oxidation of ethylene with ozone. But anyway, we can monitor the rate of a reaction by looking at the change in concentration over time for any of the reactants or any of the products. And for a chemist, it typically depends on which one is easiest to follow. Sometimes one shows up on an instrumentation analysis more than another one does. Sometimes one has a color or UV absorbance and another one doesn't. So it really is which one is easiest for the chemist to follow. But now what I'd like you to be able to do is the rate of a reaction expressed in terms of one reactant is not necessarily the exact same rate for that same reaction expressed in terms of a different reactant or a product. And so the expression we use when you are asked to compare the rate of a reaction with respect to the different substances in it is shown here. So notice that the reactants have a minus sign in front of them because the concentrations are decreasing, and products have a positive sign. Now, what you have to pay closer attention to is that whatever the coefficient in the balanced reaction is, it becomes 1 over the coefficient in the rate expression. So let me explain that. If a problem gave you, if they said, okay, the rate of this reaction with respect to hydrogen iodide is 2.5 times 10 to the minus 4 molar per second, okay? You wouldn't do anything to it. That is the rate they gave it to you. Don't divide it, multiply it by anything. However, if a problem asks you to compare the rate of one reactant to another one or to a product, this is what you need to do. And the generic formula for that is as shown. Whatever the coefficient is for the substance, again, it's 1 over that coefficient. All right, in each case. And again, remember to put a negative sign in front of reactants, positive sign in front of products. Now, the reason it's 1 over the coefficient is because you were trying, see all the equal signs? You're setting all of the rates equal to each other. And to do so, you've got to compensate for the ones that might be faster. So let me show you a very simple example. Let's say we have a reaction where the reactant is A, and 1A forms 2B. All right, so first of all, I want you to realize that if I asked you is the rate of this reaction faster in terms of A or faster in terms of B, or is it the same? So the first thing to understanding this is that the higher the coefficient in the balanced reaction, the faster that substance changes. Faster the change. Higher the coefficient, the faster the change. So in this case, B would disappear or change, up here, not disappear, sorry, it's a product, would appear 2 times faster than A would disappear. Because for every one A that disappears, we get 2 B's. So the concentration of B is going to be twice as fast as the concentration of A. So back to that rate expression. If we're going to set them all equal to each other, and we know that B is twice as fast as A, in order to make them equal, we've got to divide the rate with respect to B by 2, since it's twice as fast. So that's why that coefficient is showing up in the denominator. Now we're going to do some simple math with this expression so that we can compare rates, but it's important to understand the basics of it first. So here's a sample problem. We're looking at this chemical reaction, and this might be a typical free response question. Part A, express the rate in terms of changes in all the reactants and products. So again, all you have to remember is to put a negative sign if it happens to be a reactant. And then take the coefficient, and it's 1 over the coefficient times the rate, which is always change in the concentration over change in time. Oxygen just has a coefficient of 1. You can put 1 over 1 if you want, or just leave it out. So this would be the answer to A. Now we're going to do a little bit of math with that. Here's the second part of the question. So they are giving you the rate of reaction with respect to oxygen. So they're saying the rate that oxygen disappears is 0.23 molarity per second, or they're expressing it as moles per liter second. Okay, so they're saying if oxygen disappears at that rate, then at what rate is water changing? This equation is simple and straightforward enough. You don't really have to show your math, but I want you to know how to do that because it won't always be so straightforward. It could be a combustion reaction where you have coefficients of 5 and 13 or 26, and so you'll have to do a little bit of math. But what I want you to do first is look at this equation, and if I asked you, is the appearance of water faster, slower, or the same as the disappearance of oxygen? Hopefully you could say, okay, because of this 2 in front of water, the rate with respect to water, the change in the concentration of water is going to be 2 times faster than the change in concentration of oxygen. And so you could literally just take the rate that you were given for oxygen and multiply it by 2, and that would give you the rate of change with respect to water. So now let me show you how to do it the math way so that if you're asked to show your work or it's a little more complicated, you're able to do it. First, you can write the generic, we just wrote the generic rate expression on the last slide for all of them, but really all you need to focus on are the generic rate expressions for the 2 components they're asking you for. So I'm going to rewrite those. So, change in concentration of oxygen per unit time, and that's a reactant, so I'm going to remember to put the negative sign there, equals 1/2 change in concentration of water per unit time. All right, so make sure that you could recreate this. Now, what we're trying to do is we are trying to solve for the rate with respect to water. So this part that I just circled is the rate with respect to water. This 1/2 is an equalizing factor. It's not the actual rate. So we just want to do a little bit of algebra now, and we want this rate by itself. So how do we get rid of the 1/2? Just like you do in algebra, multiply both sides by 2. So this tells us that the rate with respect to water is 2 times, and the opposite sign, right? The rate with respect to oxygen. All right, and then you just plug in what you know. Just rewrite it. Rate with respect to water equals 2 times, and the rate with respect to oxygen was given to us in the problem as 0.23. So the rate with respect to water is 0.46. Okay, just like we could find intuitively earlier on. I want to take just a moment to talk about the signs. I told you earlier that if it's a reactant, the rate is a negative value because the concentration of reactants are decreasing over time, and that if it's a product, the rates have a positive sign in front of them. But I want you to look at the wording of this. It wouldn't be as important on my exam, but on a standardized exam, notice they say, at what rate is water increasing? So by this use of this word increasing, they have already accounted for the fact that the rate with respect to water is positive. So really all they're looking is for the absolute value of the rate, which is 0.46. That's kind of semantics at this point. Just keep in mind that sometimes a question is asking you, if they just said, what is the rate with respect to water? You'd have to put that positive sign to show that you know it's increasing. But if they already incorporate a word, increasing, decreasing, they're just looking for an absolute value. All right, almost done here. So the whole kinetic theory of chemical reactions is based on something called the collision theory, which simply says that reactants must collide in order to react. But not only must they collide with enough energy to overcome the activation energy. So remember what that looks like, right? So that's the activation energy. So reactants have to collide with enough energy to make it all the way up here. And they also have to collide with the correct orientation. So you know that when you have a chemical reaction, you're breaking some bonds, you're making other bonds. Well, if you're making a new bond, then the two atoms involved in that have to be close to each other, right? Or it's not going to happen. So, for example, let's look at the bottom one, which is correct orientation. This I have a carbon oxygen, I guess, is trying to take or is going to end up bonding with one of the hydrogens from the nitrogen group there. Sorry about that. I'm almost done. And so when these two molecules collide, they have to collide so that the carbon and the hydrogen it's trying to bond with are somewhat close to each other. And if that's not the case, then it's an ineffective collision and a reaction won't occur. What are some of the factors that can affect the reaction rate? Well, we know it's energy. We just did that in the last slide, the energy. And we also know it's the orientation of collision. But on a more macroscopic scale, the concentration of the reactants matter. Okay, so the higher the concentration, the higher the rate of reaction. So this is just a little proportional sign. It's just telling us that the rate of reaction is directly proportional to the concentration of the reactants. Because obviously, the higher the concentration, the more collisions are going to be, and therefore the faster the rate. The physical state is also important. So it's a lot easier. That's why most chemical reactions take place in solution. They're both in the same physical state in solution. They're more likely to interact and collide with each other. There are actually some reactions that occur with two solids. You can shake the solid particles together. It's kind of cool, but that's not it's not that usual. So that's what the left diagram is showing here. It is showing a clump of solid and then liquid molecules surrounding it. They're not as likely to react as if you were to dissolve that solid into the solution. They're more likely to move around and interact then. And temperature, which is a form of energy, right? So obviously the higher the temperature, the faster a reaction rate's going to go. And that is simply just given the reactants the energy they need to get over the activation energy. And finally, catalyst. You've probably heard of a catalyst. That is something that is added to the reaction that it speeds it up but is not consumed during the reaction. So what a catalyst does is it literally opens up, it's a new pathway. So like if you're trying to get the other side of the mountain, if you drilled a hole through the base of the mountain, you'd be creating a new pathway, which would require less energy. Well, that's what a catalyst does. So notice here, if you have a catalyst, the activation energy is literally lower than if you didn't have the catalyst. That is it for Introduction to Kinetics.